Hi folks, it's me, Funman. So today we'll be going through Antarctic Ozone Hole. Now before we start, let's do a toast. Let's have a cup of tea. Alright, so in the previous episodes, you heard from me what it means by an ozone hole is just a thinning of the ozone layer. It doesn't mean emptiness. There are still O3 molecules residing that area here, but compared to the reference value, it is just a bit thinner. That's why they call it ozone hole, to increase the intensity of the alarm to the politicians or the policymakers so that they will do something. And also to recap a little bit, we also talk about what are the agents here, primarily the CFCs, the chlorofluorocarbons, and the HCFCs that could destroy the ozone layer that means so much to us. So we'd like to talk about the ozone content over Antarctica and why is the Antarctica important here. Recall the Nobel Prize winners Molina and Rowland. Their work report led to certain restrictions on the CFC release during the late 1970s and the early 1980s. So, but not until 1985, when the real shock came. So what is the real shock here? That we find that there's a hole, compared to the other regions in the world, that they created some real urgency for the international negotiations on this release of CFC restrictions. And then came this Englishman by the name of Joseph Farman and his colleagues noted that there was a drastic depletion of the ozone layer over the Antarctica called the ozone hole, as you see in this figure, and the depletion was at least periodically far greater than expected from earlier calculations of the CFC effect. So when Joseph Farman and his colleagues did this calculation, it was far worse than what was calculated before here, So the debate among researchers now intensified because you have a conflict in hypothesis. One says, okay, it's serious but a bit mild. The other says, very serious. So who do you believe here, So was there a natural climate change here? Was it a natural climatic variations? Or is it due to some chemical decompositions brought about by mankind? So whose fault is it? People are trying to pinpoint the blame to either mankind or just nature, So thanks to pioneering work by many researchers, and among them Croxon, Molina, Rowland, for their work they were the recipients of the Nobel Prize in 1995 in chemistry, as well as Susan Solomon. This is a female scientist here. It's a pity that she wasn't awarded the Nobel Prize, but she was one of the pioneers as well, alongside with James Anderson, both from the United States of America, that now this complete picture is clear, The depletion is caused chiefly mainly by the ozone reacting chemically with chlorine and bromine from industrially manufactured gases, which means mankind. Without mankind, there's no factory, there won't be production of chlorine and bromine radicals. So here you see the southern hemisphere total ozone, potential vorticity on the 460 Kelvin, potential temperature surface, temperature on the 50 hPascals pressure surface, 22nd August 21 here. For the northern hemisphere, total column ozone, in the same conditions, 460 Kelvin, 50 hPascal, So what do you see here? Southern hemisphere, and northern hemisphere in the contrast here. So these white lines with arrow on the PV images are streamlines, where the thickness of the streamlines and the size of the arrows indicate the strength of the local flow. So this page talks about the stratospheric polar vortex, This is the large-scale region of air, that is bound by the wind. So it's the west to east jet stream that circle the polar region due to difference in pressure. So with the low values of ozone and cold temperature, these are the observations associated with the air inside the vortex. Now the next part here, the surprising rapid depletion of ozone layer over the Antarctica could not just be explained by the transport processes or by the gas phase chemical reactions. So the alternative mechanisms that must coexist, which could accelerate the decomposition of ozone, And this is contributed by Croxon and colleagues, They have identified the mechanism to be chemical reactions on the surface of cloud particles in the stratosphere. So these cloud particles act as a surface like a catalyst here for this reaction here. And what is it about? The Antarctic ozone depletion, right, seems to be connected to the extremely low prevailing temperature, right? When you have low temperature here, what happens here? Right, you're bound to have some particles existing. What kind of physical reactions there? That's right, condensation. So what condense? Water, right? When water condenses and reacts with the nitric acid, there's a secondary pollutant. They form the polar stratospheric clouds. We call it PSC. Okay, so these ozone decomposing chemical reactions are greatly reinforced by the presence of these cloud particles because they act as the seat of nucleations here for the site to react, and they concentrate the chemicals for speedier reaction. Now, so this understanding has led to a very exciting new branch of atmospheric chemistry here. We call it the heterogeneous chemical reactions on the particle surface chemistry. Okay, so you see that, right, there are three main types of this PSC, the polar stratospheric clouds here. We call it, first of all, the nacreous clouds, the mother of pearl clouds. They're just as very spherical like pearl, and because it's iridescent, 10 to 100 kilometers long, several kilometers thick. Can't even count it here because it's in the stratosphere. And these are mainly made of rapidly cooling water ice and glow like seashell, very iridescent in this kind of picture here, right? So beautiful, shiny, reflects like purple in nature. And the second type of this PSC contains nitric acid trihydrates here instead of pure water. So when you see HNO3.3H2O, trihydrate means 3 moles of H2O relative to the HNO3 instead of just pure water. Now the third type of PSCs are the larger versions of these nacreous clouds, but have no iridescence due to the slower rate of their formation. So you can see that, right, it is just the same color here, purple, shades of pink, shades of peach or red, but it doesn't iridesce, means, right, it doesn't reflect light and there's no shimmery kind of feeling. So I would say that the synonym for iridescent is more shimmery. So you see something, it doesn't glow, it's not it is not fluorescent, but when light hits it, does it reflect a kind of wavy kind of reflection? So that's iridescent. So with that, I'd like to conclude this part under Antarctic ozone hole here, right? And just for information that, right, these iridescent PSCs are formed mainly in winter, and that's why in Singapore you do not observe it. You need some kind of ice, right? And it's very intense in the South Pole. But if you have a chance here, please pay a visit for some expedition. So we close here, and I would like to see you in the next segment. Okay, and we talk about why there is a reservoir of the chlorine near the Antarctic ozone hole. Okay, cheers.